In the previous presentation, we did introduce a concept of indefinite integral or antiderivative. Now the challenge is to introduce definite integral. And even though they sound almost identical, indefinite integral versus definite integral, by the definition, they are completely different concepts, completely different creatures by the definition. Indefinite integral means antiderivative, derivative backward, comparing to calculus 1. Definite integral means, by the definition, area under the curve, the function curve. So this is the blue function, and the area under this curve above x-axis. This area is called definite integral. Okay, so antiderivative and definite integral by the definitions, their definitions are completely different. Definite integral represents area. Indefinite integral, antiderivative, represents backward derivative. Okay, so let's introduce definite integral. So that is simply area under the curve, the given function curve, the blue curve, blue function. So it turns out that there is no way to calculate this area using geometry. There is no way if it's a curve, unless it's a piece of straight line, then we can calculate area of a triangle, area of a trapezoid, rectangle. What else can we do? Circle, ellipse, but that's it. We cannot calculate this area even under this nice smooth curve. Okay, and Riemann invented the way how to resolve this issue, to calculate area under a curve. Okay, and the idea is really simple. Approximation. Let's approximate this area under the curve with a bunch of rectangles. Let's build those rectangles. For example, let's consider a few options. And I got lost with my windows, and let me pick a color. Let it be green. Okay, color is here. Then, for example, let's split this area into two rectangles. Approximate this area with two rectangles like that. That would be terrible. That would not be approximation at all. The area of those two rectangles has nothing in common with the blue area under the blue curve. That would be really bad approximation, not approximation at all. Let's get rid of it. Now, well, what if we, green doesn't work well. So let me try red now. What if we split the area, try to approximate the area under the curve with, let's say, 4 rectangles. Something like that. Now we have 4 rectangles. It's obviously better than before, but it's not good at all. The area under all these 4 rectangles obviously is not a good approximation to the blue area under the blue curve. Let me get rid of it too. Now, what if we approximate this area with 8 rectangles as on the picture? That is better. That is better. That is better. And what is f of 2.5, by the way? This is the function f of x, the blue function. And f of 2.5 is here. That is the height, this height. So times 0.5. What's 0.5? That is the base of this rectangle. So this product gives us area of the first rectangle on the left. That's the area of the second rectangle from the left, and so on. 8 of them, 8 rectangles, 8. 8 rectangles gives us more or less approximation of the area under the blue curve. Okay, now so this sum is called Riemann sum of the areas of the rectangles, and there are 8 of them in this example, and this approximation is definitely not perfect, but Riemann said, let's take a limit. It means number of rectangles goes to infinity. Let's consider not 8 but 8 millions of rectangles. So we may say let's consider limit number of rectangles goes to infinity, or alternatively we may say the base of each of the rectangle becomes smaller and smaller and smaller, and the rectangles become skinnier and skinnier and skinnier. It means the base goes to 0. That's the same as number of rectangles goes to infinity. So if we consider this limit and use our imagination and intuition, that we can believe, so then we can say yes. So this limit, theoretically, this limit will give us an exact area under the curve, under the blue curve, on the interval from x is equal to 2 to x is equal to 6. Okay? So this approximation, if we consider 8 million of rectangles, it will give us really good approximation to the exact area. That's what is called Riemann sum. That's what is called definite integral. So definite integral out of the function f of x on the interval from a to b. What's a? It's equal to 2 in our example. What's b? It's equal to 6. Oops. It's equal to 6 in our example. So it means calculate area under the curve f of x, below the curve f of x, above x-axis, from x is equal to a to x is equal to b. That's what it means. So definite integral is defined as area under given function curve. And the way to calculate this area is tricky. It's a limit when n number of rectangles goes to infinity, or alternatively when the base of each rectangle, this base goes to 0, becomes smaller and smaller and smaller. The rectangles become skinnier. It means number of rectangles goes to infinity. Then intuitively it's clear that this limit will give us the exact area, which is equal to definite integral by the definition. But the problem is, even if we take the most powerful computer in the world, and this computer will not be able to calculate the exact value of this limit, this computer, regardless of the power, will not be able to add up infinitely many rectangles, areas of the rectangles. It will give us a very good, maybe even perfect, but approximation, not exact value. Anyway, so that was introduction of the formal definition of the definite integral. What's definite integral? That is a limit of the Riemann sum. That is the formula on the top, on the bottom, almost bottom right. So this is definite integral. This is notation for the definite integral, which means area under the f of x curve, the blue area, on the interval from a to b, from 2 to 6 in our example. And this area is equal to limit out of the Riemann sum. And this limit is limit out of infinitely long summation of the areas of the rectangles. It might be calculating using computers. It cannot be calculated exactly. This is theoretical definition of the definite integral. Simply speaking, definite integral, it's equal to exact area under the given function curve. And it's introduced as a limit out of the so-called Riemann sum, which is simply, what's Riemann sum? That is the sum of the areas of all these triangles. Okay, and the limit out of this sum when number of triangle goes to infinity and or base of these rectangles goes to 0, this limit will give us exact, theoretically, will give us exact area under the curve, and it will be equal to definite integral, which represents area under the given curve. We're done with the introduction of the concept, important concept, calculus 2 concept of definite integral.